All right, guys, I'm gonna start catching up to you. I haven't done any of this yet, so I gotta. Oh shit, I'm way behind. So in the middle here goes 966.84. What can I put right below that? Zero. Kick ass. And then you can find 930 and 1200. So I want the area between those. So this is that one that I try to make complete physical sense about the fact that once I get the areas, I just subtract them to get what's in the middle. So before I can get the areas, I gotta change these to z-scores. Not gonna be as easy as this guy was. Shit. So I gotta use the z-score formula twice. Once on 930. And another time, what is it? 136 times. So you guys got what? Negative 0.27?
Yeah.
And then for this one, you would put 1200 in. Blah, 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 blah. What'd you get for this one? I forgot. 1.7?
Yeah.
Yeah, I guess I did. So that's a little more than a quarter of a step down, and this one is almost 2 steps up. That's the interpretation of those. And I just look them up, get the areas. Never subtract z-scores. I don't know if I've said that in here yet. A z-score tells you where you are. If you subtract them, you are somewhere else. You will answer a different problem than what I ask, and you will lose points, many. How many? Many. So if I look up 1.7, or if you look it up, what did you guys get? 9554? Sounds about right. What about negative 0.27?
3936.
3936? That sounds familiar. So then I have to take 0.9554 minus 0.3936. And what'd you guys get?
0.5618.
Kick your ass. So what does that mean?
That's the probability.
That probability between.
I like it. What's an even more? So here's a way to say that a little bit more. About 56% of 3-bedroom flats in the Taupo district of Waikato, New Zealand, cost between $930 and $1,200 a month. I like it. Sweet. This guy is the reverse of this guy. Can somebody tell me 930? What percentile is that?
39.
A little more than the 39th percentile. Do you guys see that?
Right.
Because again, what does percentile mean? The percentage below that thing. So what percentile is 930? It must be in the 39th percentile because there's about 39% below. So where would the 15th percentile be? It's only supposed to have how much below? 15%. It's only supposed to have 15% below it. So it's got to be down here. So it only has a little 15% in there. So is it going to be a positive or a negative z-score? Negative z-score. So I know to look on this side. And I don't have a z-score yet. I have an area. Where are the areas on the chart? In here. I like it. Normally I look up a z-score, get an area. If I have an area, I can look out to get the z-score. So where's the closest to 0.15? Yeah. Is everybody cool with me? Do you guys see this? This is 15 away from 15. This is 8 away from 15. That's close. Right? So negative 1.04 is the Columbus number. Right? 1492? No? No kids. Negative 1.04 is that z-score. Let me say this a different way. If I go down a little more than a step from the mean, I have 15% of the data below that. So if your z-score on a test was negative 1.04, that means that 15% of the people scored below you if they're normally distributed. You would be in the 15th percentile. Now, I asked for a rent. This, unfortunately, is not a rent. I wish somebody would pay me $1.04 every month to live somewhere. Thanks for living here, man. Here's $1.04. That's not much money, but shit, it's better than paying $1,400, $1,500, $1,600, $1,800. Unfortunately, it's not a rent. How do I make that back into a rent? X equals mu plus z sigma. It's the backwards equation because I know z and I want to figure out x. So the mean is 966.84. The z-score is negative, so I'll go down this many steps. What were they? 136.91. So if I start at the mean and I go down this many steps, I'm going to end up at the 15th percentile rent. So what do you guys get for that? 824?
Yep.
45? Don't forget the 45 cents. I like it. Why did I write that sideways? I don't know. Now this one really trips people out. Don't blame me. I mean, the mean is so low and the standard deviation is really small, so to get up to 1600 should be almost impossible, to be honest. Let's see what we got. So 1600, weigh the shit up there. I want the area above it. When I make this into a z-score, what'd you guys get?
4.62.
Now, at this stage of this class, I hope that a few of you at least could look at that and go, holy shit, that's really far up there. 2 steps is where unusual starts. That's frickin' more than twice as many steps away. Holy shit. That would be like the dude that's almost 8 foot tall. You'd be like, damn. And then the guy's like, I know, right? If I was almost 8 foot, I'd just say that. Damn, I'm like, I know, right? This is crazy. You guys semi with me. So that's like unusual to the next power. So that, what percentage should be even further away from the mean than 4.62 steps? Almost nothing should be that much further away, right? Most of it's within 2 steps, and this is like more shit. So when you look at the chart, though, it's a little bit freaky. The chart sort of gives up, right? Look at the chart, it goes, all right, I got everything, oh shit, I'm tired, man. You guys see this? So where is that on the picture, though? Is that the answer? Hell no. Whenever I look up a z-score, I get the area that is below. So what's the area above?
1 minus.
Yeah, 0.0001. Now to be. Now that's fine. That's beautiful, right? I wrote it down. That's the answer. In reality, the further I get from 3.5, there's not just this much. There's more than this below 4.62, right? So I would actually say approximately 0%. So I would accept this answer right there. Or you can just do it with a chart, because I gave you the damn chart. I better let you use the damn chart. So I would take either one of these answers. So if it's off the chart, then it should be like 100% below it or about 0% above it. All right, I like it. All right. So this guy, now we're in San Diego, unfortunately. In terms of, I mean, it's great here. It's really great, but shit, do we pay for it? So you guys might be able to relate to this. So San Diego, these are, I just looked these up, by the way. And this is what I kind of estimated, but oh. So find the probability that it would cost between 2,000. So again, what goes in the middle?
Mean.
Which is 2703.74. Then 2,000 is like right there, and 3,000 is like right there, right? So I want this area. So it's just like the first question up here. Just we're not in New Zealand, we're in San Diego. So then I make a z-score out of 2,000. Z-score out of. What do you guys get? Anybody get this far?
-2.00.
Is that right? Is that
Yeah.
27? Okay, yes, I agree. Negative 2 point. Oh yeah, this is the one that comes out to be like this, right?
Yeah.
Here's the crazy thing about rounding that you don't hear very often. Screw the decimal place. Take it out. Is that closer to 199 or 200? 200. So it's negative 2.0 up. When you're rounding, you can ignore the decimal place at first and then throw it back in. Then it's so much easier to look at it. This always freaks people out. Because it's sort of like the odometer flipping. That makes that go up to 0, that makes that go up to 0, that makes so it's like dominoes going back, but it's much easier to just go 199 point, okay, that's 200. So negative 2.0 up. Kick ass. A little bit. And then what's the z-score for 3,000? 3,000 minus blah, 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 all the same shit, right? 0.84. Okay, I like it. I'm getting agreement. So I'm going to look up negative 2. What's that?
0.0228.
Yeah, I like it. I'm a little scared that I actually remember that number. And then 0.84, what do you guys get for that one? 7995. That sounds familiar. So then how do I get the area between?
Subtract.
I had a question in my other stats class that said, do you leave it negative or make it positive? The answer to these questions can never be negative, right? Probability cannot be negative. Area can't be negative. So it's always bigger minus smaller. Can a z-score be negative?
Yeah.
Of course, we just got a negative one, right? Just means it's below the mean. But areas and probabilities can't be negative. So what do you get here? We get 0.7767?
Yeah.
Yeah, Jeff. So about 78% of 3-bedroom apartments in San Diego cost between $2,000 and $3,000 a month. Now notice this, it was almost impossible for a place to be more than 1,600 in this district of New Zealand. In San Diego, what's the percentage of them that are less than 1,600? That's what this is really asking for, right? So what do you get for a z-score for this?
Negative 3.13.
Yeah. And when you look that up, what do you get? 0.0009. Which to most humans would be almost impossible, right? That's what that means. About 0 again. Okay, I like it. Don't go moving to New Zealand though necessarily. I'm sure their average income is probably lower, maybe. It's where they filmed The Hobbit, so hey, what the shit? They live in the Shire. Okay. Now. Any questions from that? So at this point, we have done a lot of normal curve problems. Right? Yeah, we're about to take the next step, yeah. I don't know if I'm going to quite get to explaining that yet, but I want to start with the idea. And some of you guys are like, you can't just tell me how to do the problem. All right. Somebody back there turn that one light back up. Thank you, sir. All right. Every problem we've done so far with these normal curve things has involved picking one person or one thing, right? You guys understand what I'm saying? Find the probability that this person's grade is less than this. Find the probability that this one rent is more than this. Some of you guys are like, keep going. But does everybody agree with me? That's if you look back at every problem we've done so far from chapter 6, they've all been like that. So that's fine. That could sometimes happen. But what are we normally working with in statistics? What's the first step in almost any statistics problem? Take a sample. So for example, if I wanted to check to see Let me see, what's a good example? So let's say I just hire this new guy and they're supposed to cut these pipes to a certain length. You with me? So that they'll fit. So they don't have to be exact, but they have to be close to a certain length. So if I wanted to check his work to make sure that he was doing well, is it possible that the best pipe cutter dude could make kind of a mistake on one pipe? And they're still a really good pipe cutter, right? But they could make a mistake on one pipe that's not going to kill him. I'm not going to fire him because of that. You with me? Does this make sense so far? What is it then that could help me? So I can't look at one pipe and tell if somebody's good or not. It's sort of like somebody's like, I know how to play basketball. All right, take a shot. If they miss, I might like, you don't know how to play basketball. If they take one shot. If they make one shot, does that mean they're really good? No, it might mean they're lucky. If they miss one shot, does it mean they're really bad? No, it might mean they just missed that one shot, right? You guys with me so far? Okay. So how do I really check somebody's work or somebody's claim? I really need to ask, I need to take a sample of stuff and then check to see if that's within the right place. So if somebody takes 50 shots and they make one of them, is that evidence that they are not good? Yes. See, I didn't say it's proof. I said it's evidence. It's really strong evidence. If they take 50 shots and they make 48 of them, that's strong evidence that they're good. At least they're taking shots, right? No, yeah, I don't like that. So we have a method of investigating a single value to see if what the probability is that that single value will be greater or less or in between two things. We have mathematics for that. We have an ability to do that. What I need to develop is, what if I take a sample of pipe lengths that this one pipe cutter does, and I want to show evidence that he is not a good pipe cutter. So I got to show evidence that they're too long or too short. But it's not just one pipe, it's a sample of pipes. So what we're about to do, before I get into this, I want you to understand why we're doing it. I've got to see how the math is going to change when I'm talking about a group of things, not just one thing. That's all I can do at the moment. Thank God, let me give you a little spoiler, the work we do is not going to change by very much at all. It really isn't. It's going to be remarkably small change we got to make. We're not going to get there for a while though, because there's a lot of freaking concept behind it. Oh shit, that means Jeff is going to talk a lot. So just get ready. All right. So let me ask you this, just to kind of get there. If I went out right now and I picked just a random person, I drive around San Diego, I randomly stop and I randomly go out and I randomly pick somebody. If they were 5 foot tall, would that freak me out? No, right? Right? That's below average, but not like you're not going to go, he's 5 foot tall, holy shit, get away from me, you're weird. No, right? Or wow, you're 5 foot tall, what's your story? What's going on with me? If I went out and randomly selected 60 people, and their average height was 5 foot, would that freak you out? Now you can tell what I want the answer to be from the way I'm talking, right? But still, think about it. That really should freak you out. If I take a random sample of people, their average height should be close to the real average. Let me say that again, because that's huge, what I just said. Any group of things I pick, if I randomly select them, their average should be close to the real average. You with me? If you take 80 Grossmont students at random and take their average age, it probably won't equal the average age of all Grossmont students, but it should be close. And if it isn't close, you got to go, wait a minute. Maybe that's proof that the average they say is wrong. Okay, maybe. Sort of like proof that the pipe cutter sucks, right? If I got to collect enough evidence. Okay, so let me do my little spiel here. I think I've done this. Somebody told me I'd done this picture before, but we're going to reanalyze it again. Two little mounds of shit up your butt. Shit emoji. So this, I think I did this before, but I want to use it in a different way. I think I did this with Chubby Dude theorem in here. Chevy Chev's theorem? Okay. Now we're going to look at it for a different reason. This is still ages in Florida, right? So let's say that I go down to Florida and I ask individual people how old they are. Or maybe somebody who's in charge of them, because if I say, how old are you? They're not going to say, 2 months old. No, I'm going to probably have to ask. So that would be this person right there, right? Put a dot. And so why is this tall? Because there were a lot of people who were that age. How many people are in here? Nobody. Just randomly, right? And let's say that the oldest person in Florida is 100 because they have this weird Logan's Run thing where they kill you once you're on. Have you ever seen Logan's Run? That's fine. It's an old movie, kids, but it's still good. Anyway. So what would be a good guess for the mean here? 50. All right. So let's say that it happens to be 50. Okay. I like it. Everybody with me? Is this normally distributed? What's normal look like?
Curve.
I like it. I like it. And that is not that. Everybody with me? Okay. Now, this picture was created by me talking to not single people, they might be married, I don't give a shit, but one person at a time. What's your age? Plot it. What's your age? Plot it. What's your age? Plot it. Right? How old are you, huh? 97. All right. So I want to do this again, but realizing that statistics, we normally use samples. So let me go back to Florida, because I got all kinds of time, and I didn't learn not to go back there because I lived there before, and I know better now not to go back. But let's say I go back, and I don't talk to individual people. I talk to groups of 10. And I take a group of 10 people, and I say, what's your average age? And everybody works, and they give me their average age, right? Maybe I'd check it to be sure. It says Florida. Right. So now I'm going to go back to Florida, and I'm going to say, take groups of 10. See if I have any marker. I think my red marker is my best one right now. There you go. Oh yeah, get high. There you go. Now I'm going to talk to 10 people. I'm going to take their average age and then plot it. Talk to another group of 10 people, take their average age and plot it. It is not going to look the same as that. Why? What's the most likely thing that will happen if I take a group of 10 people? Is it very likely that I would get a bunch of old people, 98, 99? Is that going to happen if I'm randomly picking? Could that happen? Yes. Is that likely to happen? No. What is the most likely sample I could take? Would be made up of a mixture. Does that make sense?
Yeah.
The most likely thing is I get a few people from over there and a few people from over there. Now let me ask this next question. What would you expect the average sample, the average of your sample? What would you expect? Each sample, you would expect it to be close to what? If I take a sample of people, their ages should average to be close to what? The average of everybody. We talked about that earlier, right? So this is kind of neat. Stay with me. You guys semi with me? When I go to plot this now, I should have very few things down here, very few things up here. Most of the stuff is going to actually be right there because most samples should be a mixture. So the highest point should be like right here now. Because what am I plotting on this other picture down here? I'm plotting the averages I get. So if I get a bunch of young and old people, their average is probably going to be close to 50. And that is what's going to happen most. So shouldn't that be where the new peak is? And then there might be a little hump down there for this guy, and there might be a little hump up there for that guy. But that's basically what it's going to look like. Now, to be honest, that colorful side, I'm not referencing it totally yet. We're not going to talk about it yet, but the colorful side, it's got a specific example of this. Because you could sit there and go, yeah, you're just saying that shit, Jeff, but that doesn't necessarily happen. But you can see how this makes sense, and that actually is a concrete example of it happening.
So could you consider that the denominator distribution?
Not quite, but it certainly looks closer than it did.
So what would you call that?
I would call that the distribution of ages. But it is closer. Now that's going to become part of this. So this guy here is the standard deviation. This guy, let me see if you guys are cool with this. This is what is this a plot of again? What was I plotting there? Good, averages of samples, right? So let me see if you guys are cool with this. Let me make this big. I'm going to call this guy standard deviation. I'm going to give it this symbol. It's the standard deviation of the sample means. Have you guys ever noticed in your calculator when you do 1 bar stats and you look at S and sigma, what's it got right here? Because that's the standard deviation of individual data values. We normally don't put that when we write it because it's just understood that that's what that means. But this one is not for individual data values. This one is for groups. This is for samples. That's how I distinguish between these two.
You said on the graph, what is it equivalent
What?
to? I said, what is that equivalent to? Like, what does it mean?
The standard deviation of the sample means.
Oh.
And this is the standard deviation of the individuals. How did I make this picture? By talking to individual people. How did I make this picture? By talking to groups and taking their averages. Which one of these has a smaller standard deviation? Let's see which way I want to go. Which one of these has a smaller standard deviation? What does standard deviation mean? What does it tell you? What does standard deviation tell you?
Distance from average.
The average distance from the mean to the data points. So, if I'm asking you which one has the smaller standard deviation, which one has data points that don't get away from its mean as much? Second one. Didn't it kind of squeeze this? Right? And then it becomes this. That's exactly the sound it makes when you do it. You guys are loving this, I know, but I know I'm leading you in a direction because all this shit's been settled already, but I want you, as my fellow humans, to agree with this kind of makes some sense. Just saying that. I haven't told you exactly how smaller, but you can definitely should agree with me that the spread here is less than this. And here's, now, what if I took, so this is a sample of 10, right? Here's what gets interesting. If I take a sample of 30, oh, that's it. Take a sample of 30, the picture will look like this now. Because now with a group of frickin' 30, it's going to be even less likely to just get a bunch here to go a little hump here. It's going to be even more likely that you do get a mixture. So now there's going to be a lot more around the mean and a lot less at the extremes. That sounds like around 30, it starts to get very normal. Why is it really good to know when the distribution I'm working with gets normal? Because once it's normal enough, I can get all the frickin' answers from that chart I gave you. The chart kicks ass. It's all the answers. But what do I have to know? That I have a normal curve. So with these kind of problems, how do you know when it's normal enough? Well, to be honest, it's if n is greater than 30. Once n, the sample size, the number of people I'm picking at a time, like a group of 31 and a group of 31, and once I plot it, it's going to be normal enough.
When it reaches 30 or it's
A greater than 30, yeah.
Is it for every type of problem?
A beautiful question. It doesn't matter what the hell the distribution looks like. This distribution, to be honest, is nice because this distribution is kind of symmetric. So it would probably start to look normal before 30. But that rule is for any distribution. It can look like whatever the shit you want it to look like. After you get 30, it's gonna, oh, nice. And then I'm allowed to use the z-score chart to get the answers. So in stats 1, if this was my distribution, I can't do shit. Because I don't know what the hell do I do with that? It's not normal. I got nothing. Stats 2, you start to learn about what you can do with this. And unfortunately, we don't teach stats 2 here. Maybe someday I'll make a stats 2. That'd be awesome. And you guys are like, great, Jeff. I won't take it. All right. So here is. Let me do this. I'm not going to tell you this.
So greater than 30. How do you go?
Greater than 30. Yeah, I'm sorry, but I just want to say around 30, it will start to look like this. So the official rule to cover all the weird ass distributions is greater than 30. So look, what happens to the mean? Does it change? So if I took each person in here and got an average age, would that be different than taking 2 people at a time and averaging all the averages? It's going to be the same freaking numbers, the same freaking people, right? So the average will stay the same. The standard deviation will change. So we're going to look at this. Let me see. Ooh. We're going to look at this. Starting a little bit right now, and then I'll let you out in a few minutes. Just don't freak out. So we're going to really analyze this next time. I don't want to try to shove too much more into your brains. But do you see how if I put these numbers in a hat, does everybody agree with me that that's basically what the distribution would be, right? If I put the numbers 1, 2, 3, 4, what's probably pick any of them? 25%. So I drew it as a histogram. That kind of looks like a uniform thing, right? So this is this normal? No. Is it nice? Yeah. I really want this, I sort of said this earlier. The nicer it starts off as, the smaller n can be and it already starts to look normal. As if it's really disgusting, n has to get above 30 to make it finally look normal. So now, what I did, God, I gotta get to the point of this. You guys are like, just let us out, Jeff. What I did was, if I reach in and take 2 with replacement, because without replacement, things get freaky as shit. So I take, what's one thing I can get? I can get a 1 and then another 1. And what's my sample mean? 1. Or I could have gotten a 1 and then a 2. And what's my sample mean? 1.5. So this is a small enough problem that I was able to list all of the possible samples. There they all are. You guys cool with that? That's all the shit that could happen. I like it. And so what I did was, see how there's 2 1.5s? So it's got a 2 out of 16 chance. There's 3 2s, there's 4 2.5.